All right, welcome to your AP Unit 7 Solubility Equilibria problem walkthrough. We're going to start with question 11, problem 4 as a conceptual kind of warm up, and then we will jump to finishing AP question number 1 on page 7. And we're going to do the whole problem I think we've already started in a previous video, one part, but yeah. So starting with question 11. Oh, and of course, don't forget to look down in the description box for the timestamp where the AP question begins if you feel pretty comfortable with the conceptual covered in class. So question 11, okay, we are told that sodium dichromate is used, okay, in the production of chromic acid, a common etching agent. A previous student of mine from last year, actually, shout out to oh no, what's his last name? Schoenfield, I think. You know who you are. A common etching agent. Calculate the concentration of each ion in a solution of sodium dichromate prepared by dissolving 0.50 grams in 150 milliliters of solution. So first and foremost, you need to probably write out the balance equation of this dissolution of the ionic compound into its respective ions. And then 2, you're going to notice that you aren't given molarity. So you're going to definitely have to calculate molarity. Okay, this is definitely your recipe for calculation of molarity. Okay, to get to concentration. So to begin with, the balanced chemical equation would be sodium dichromate being dissociated. So it would be an equilibrium of Na2, Cr2O7 solid in equilibrium with its respective ions of Na plus aqueous and Cr2O7 minus aqueous. And obviously to balance this, we need 2 sodium ions for every 1 dichromate. So now what you need to do is you need to calculate the concentration of each ion. Given the fact that you started with 0.5 grams in 150 milliliters. So I would just convert this to molarity of by doing some dimensional analysis. And so this would be, here, and I'm going to say of Na2Cr2O7 times for every 1 mole of Na2Cr2O7, I have a molar mass of 261.97. Okay, and then times for every 1,000 milliliters, I have a value of 1 liter. And when I do this math, okay, I got a value of 0.01272. I'll do sig fig stuff later, molarity of Na2 sodium dichromate. Okay, so knowing that, I can say, well then, okay, stoichiometrically speaking, the concentration of my sodium plus would be twice that, okay, would be 2 times that, because I have a relationship of, for every 1 dissociated solid sodium dichromate, I get 2 ions of sodium. And so what I would say is that I would say that I have 0.0127 molar times 2. And that gets me a value, because it's like times 2 Na for every 1 Na2Cr2O7. This is okay. And that would get me a value of, I have a concentration of Na plus of 0.025. Now to the proper sig figs. Okay. Let's see, 0.0254. Oh, nope, the lowest sig fig is 2. So 0.25 molarity. And then for dichromate, it would be just that, Cr2O7. Okay, it would be 0.0127 molar times, well, there's 1 dichromate for every 1 Na2Cr2O7. So I get a value of 0.013 molar. Okay. And that right there would be my responses, my answers. And that is also, by the way, a really great review of your molarity and ion concentration when you're talking about dissociation. Okay, so now let's erase that little star because we did it. And let's move on now to question 1, and let's finish up AP question 1 completely. So AP question 1, you'll notice will probably be a giant crossover with unit 3, where we even talk about solubility as well. But we've already answered in our equilibrium expression AP walkthrough, writing the equilibrium solubility constant, actually, the unique equilibrium constant for the dissociation of solids, ionic compounds, because remember, technically a solid is like saying over 1. We don't really count them. It's like a 1. So we just don't even write it. So we've done this work previously. And going to part B, calculate the value of Ag plus in 50 milliliters of saturated solution of AgBr at 298. So saturated means you have the maximum amount that will dissolve. So you don't really have to worry about calculating for excess solid or so forth, okay? So what you should see is that if the KSP is the concentration of Ag plus and Br minus times the concentration of Br minus, what we can do here is that, let's say that X is the concentration at equilibrium of Ag plus and Br minus, okay? Because we don't really have that much information to go off of. So let's say for KSP, that is some value of X. And we know they're in a 1-to-1 ratio, by the way, because Ag and Br are a 1-to-1, right? Ag plus and Br minus is in a 1-to-1 ion production ratio. So it's like saying 1x to 1x. So what we see then is that we can just put variables in for this, and we can say, well, it's the concentration of X times the concentration of X, which is equal to X squared. Okay, so that gets us to variables. And here's the great thing. If you look in the original prompt, we actually know what SP is. We are told that it's 5.1 times 10 to the negative 13th at 298 Kelvin. Okay, so that's really great. And if you're like, so far, I'm not using that 50 milliliters, you're right. You're going to wait. You're going to wait. Okay. And so what you're going to do is say, well, let's set it equal to my prompt information and my arithmetic manipulation. So I say that KSP is equal to 5 times 10 to the negative 13, which is equal to X squared. If I take the square root of 5 times 10 to the negative 13, then at equilibrium, which that whole term saturated right there helps us understand that we are in conditions that create the maximum amount, okay, of ion production. At equilibrium, we would find that X is equal to 7.1 times 10 to the negative 7, okay? And if X is equal to the concentration of Ag plus and Br, then we would say that the concentration of Ag plus is indeed 7.1 times 10 to the negative 7th molarity, okay? So if you're like, wait, I didn't need that 50 milliliters, you're right. You didn't need that 50 milliliters because here our mathematical manipulation already accounted for the 50 milliliters by using KSP algebraic, how would I put this? Algebraic, yeah, just algebraic process. So the 50 milliliters, since we're assuming it is at equilibrium, the 50 milliliters doesn't really matter for us because whatever we find for the value of molarity is accounting for the 50 milliliter condition, okay? So great, there's your answer. And C, 50 milliliter sample of distilled water is added to the solution described in part B. So again, you'll notice that this is actually contingent slightly. You'll see that as you progress, you often have questions that are contingent on the response from above, or at least connected to it. which is in a beaker with some solid AgBr at the bottom. The solution is stirred and equilibrium is reestablished. Some solid AgBr remains in the beaker. Is the value of Ag plus greater than, less than, or equal to the value that you calculated in part B? Justify your answer. So what we notice here is that some sample distilled water is added to the solution described. So here what you're doing is by adding distilled water, okay, you're diluting. Okay, essentially you are diluting in this problem. This is a dilution process. And then we're told that solution is stirred and equilibrium is reestablished. Some solid AgBr remains in the beaker. Is the value of Ag plus. Well, here's the thing. Dilution doesn't really. Oh, well, I guess, okay, it changes molarity, but let's see, which in the beakers is reestablished? Some solid AgBr. So the answer should be, and I'm pretty sure, is that the value of AgBr, Ag plus from the dissolution of AgBr after dilution or the addition of water remains constant. So remains constant or equal to the value calculated in part B. Okay. Here's why. The concentration of ions at equilibrium don't change. Like, those are the equilibrium values, and it definitely doesn't change with necessarily dilution itself. So it would only change with the concentration. Although I guess we talked about periodically. Let me think how to form this. Hold on, guys. Because I think the answer, first of all, you have access to the workbook key. So this is the answer that the AP gives. I'm trying to make sure if there's any caveats in thought that I'm missing that could confuse people. Okay, so I think I figured it out in terms of how I want to say it. So you have some solid initially, you have some solid at the end. So clearly the solid did not dissolve. So then it doesn't really matter because it didn't change it. Because, oh, duh, guys, hello, I even emphasized this before. You're at saturation. So if you added any more, you're done. You can't get more ion out of this because any more, okay, any more dissolution would actually be super saturation. So you would just precipitate out more solid and your ion concentration would remain the same because at equilibrium, you were at saturation. Boom. Okay. So that was exciting for me. So what's my justification? The value of Ag plus after dilution remains constant or equal to the value calculated in part B. The AP answer says it this way, that the concentration of ions in solution at equilibrium with a solid don't depend. Don't depend on the volume of the solution. Okay, that's the AP answer. I would also like to point out what I just said earlier is that in the previous work, you just were told that you're at saturation level. There isn't any more you can do. Then you're told in this prompt that the solid basically doesn't dissolve because there's still solid there. So obviously nothing really changed. Okay, great. So D, calculate the minimum volume of distilled water in liters necessary to completely dissolve 5 grams of AgBr at 298. The molar mass of AgBr is 188 grams per mole. So first of all, figure out the moles of AgBr given the grams. So you have 5 grams of AgBr. Okay, you multiply it by molar mass, 188, and you get a value of 0.0266 This is unit 2. Like this is literally unit 2 material. I believe this is unit 2. Okay. 0.0266 moles of AgBr. I think that's unit 2, if I recall my units correctly. And then you're asked, okay, so what's the minimum volume of water I need to completely dissolve it? Well, I know that at equilibrium, my concentration of Ag plus, okay, has to be, so like my product is the dissociated ions. So I need to have enough liquid volume added to get the AgB R dissociated ions to have the concentration of 7.1 times 10 to the negative 7th molar. So I know then that this is going to Ag 0.0266 moles of AgBr is going to have to produce concentrations of Ag plus and Br minus that are equal to 7.1 times 10 to the negative 7th molarity at equilibrium and thus saturated dissociation. And so, or saturated dissolution. And so what I say then is, well, how can I get this equal to 7.1 times 10 to the negative 7th molarity? Has to be equal to this mole value, 0.0266 moles, okay, of AgBr, which by the way is also a 1-to-1 ratio with Ag and Br, all over some volume. And then you solve for volume and you should get that the volume value that you are required is 3.7 times 10 to the 4th liters is what you need to get to a concentration of the respective dissociated ions at equilibrium from the 5 grams of AgBr solid. Okay, yeah, that's nice. So E, whew, this is kind of a long one. This is definitely a long FRQ, huh? E, so a student mixes 10 milliliters of 1.5 times 10 to the negative 4th AgNO3 with 2 milliliters of 5 times 10 to the negative 4th molar NaBr and stirs the resulting mixture. What will the student observe? So if you have so first and foremost, you want to calculate the concentration of the ions. Okay, so we have what they'll do is a switcheroo. Okay, so what you'll see is that NaNO3 pairs up, right? AgNO3 plus NaBr will go to AgBr and N plus NaNO3. Okay, that's the reaction, the double displacement reaction that occurs. And what you notice then is that, look-see-dook-see, we have the compound produced that we've been studying in this question the entire time. And we know that AgBr is an equilibrium. It is a solid, but it's an equilibrium with its dissociated ions. And NaNO3 stays aqueous. This is kind of part of your solubility memorization rules, that anything with an alkali stays associated. So there is no equilibrium here because it just doesn't ever form a solid in the first place. So this kind of ends up being honestly obsolete to us. And so then what we see is we have this AgBr, Ag plus Br minus focus that aligns with the kind of the storyline of our question. And we do get a solid out of it, but that solid is in constant equilibrium with its dissociating self. And so what we need to do now is calculate, okay, then what is the concentration of these ions? Okay, so what we see then is the concentration of the Ag plus and the Br minus that would be produced from the production of AgBr solid is the diluted molarities. So AgNO3 is the source of Ag in the AgBr. So what we would see is that Ag NO3 has a new molarity of, here, let's see, 1.5, right? Molarity. Right, and here we're doing M1V1 equals M2V2 times 10 milliliters divided by its 12 milliliter total. And that gives us a new value, okay, a new diluted value, M2, of 1.3 times 10 to the negative fourth molar AgNO3. And AgNO3 has a 1-to-1 ratio with AgBr in terms of producing Ag. And so what we would see is this is also equivalent to the Ag plus ion concentration. Okay. I hope you were tracking the molar ratio. So here, I'll even highlight this for you to color code it. AgNO3 is the source. You get 1 Ag for AgBr for every, and then from every 1 AgBr, you get 1 Ag plus. So that's kind of the track I'm following. What is then the diluted concentration of Br minus? Well, let's get into a different color. We do a similar thing, M1V1, M2V2, except here, the source of our Br is the NABr sample. So we say that NABr, we're told that it had a 5.0 times 10 to the negative fourth molarity. And we started with 2 milliliters, but now we're in a solution of 10 milliliters. And we get that we have a concentration of 8.3 times 10 to the negative fifth molarity. And again, what you should see here is that for every 1 NABr, you have 1 Br and AgBr. And for every 1 AgBr, you have 1 Br minus ion. And so that way we can say that this is the molarity of the Br minus in solution. Okay. That is a result of the equilibrium established between the solid AgBr precipitate that is actually produced, but that is also dissociating in slightly in the water. And so what we then want to observe is what is the Q value and how does this compare to the KSP? Because our question was, what will the student observe when we stir this all in? So what we would say is that, well, since this is a dissociation, we know that this is going to try to reach equilibrium. So where is it currently at? Using Q value, your QSP, quotient, solubility product quotient, and comparing it to the KSP that we actually found, and not even found, we're given above in the prompt, okay? So given these values, we would say that Q is equal to the concentration of Ag plus and Br minus, and that equals at this specific state of the reaction, and that equals, I don't have room on my paper, but it would equal 1.3 times 10 to the negative fourth times 8.3 times 10 to the negative fifth, and that gives us a value of 1.1 times 10 to the negative eighth. Molar, sorry, not molarity, it's a non-unit number. And then what we do is we take this and we compare, this is a long one, we take this and compare it to Q versus K, and K is given to us in the prompt 5.0 times 10 to the negative 13th. So we know that K is 5.0 times 10 to the negative 13th. And we would see that Q is greater than K. So that means we have way more we have way more ions, in solution right now than what should be in terms of establishing equilibrium. So what we would see is the reaction shifts toward reactant. And our reactant is a solid. So we would see that precipitate would form. Whew. And that right there is the final answer to this question. It was quite the doozy because it involved you to connect many levels of unit 3 and unit 7, and also go back in the prompt. Never forget the initial given data in the prompt. So hopefully the color coordination worked. I realized I did not leave enough room on this paper to do that thoroughly in one space. Oh, well, too late now. And again, don't forget the reason I completely ignored NaNO3 is because it was never solid in the first place. So there is no equilibrium to be had. It just doesn't ever create a solid that could be in equilibrium with its ions. Like it just stays in ions. So that's why we're able to completely ignore NaNO3 in the double displacement reaction that we are told about in this prompt for part E. Okay, finally, F. The color of another salt of silver, AgI, is yellow. A student adds a solution of NaI to a test tube containing a small amount of solid cream-colored AgBr. After stirring the contents of the test tube, the student observes that the solid in the test tube changes color from green to yellow. Write the chemical equation for the reaction that has occurred. Okay, so here is your chemical equation. You are told that you are reacting silver AgI, okay? And a student adds that as a solution of NaI to a test tube containing a small amount of solid AgBr. So actually the real reaction is NaI being added to AgBr. So it's NaI, okay, being added to AgBr, and it's a solution of NaI, so it's aqueous, and it is being added to solid AgBr, okay, and what happens is it produces, okay, AgI and NABR. And of course, you're double checking that you are canceling out your charges, making good compounds. Now you're told that when it mixes, you see the yellow. And yellow means that that is the color of a salt, according to the first sentence in the prompt. And that's a solid. So you know that AgI is a solid, and this is going to be yellow. And that NABR, we know in a double displacement reaction, you can never have more than one solid present. So you know that NABR is, so whoa, why did I write solid? It's aqueous. And also Na is an alkali metal, and you know that anything with an alkali metal is aqueous. So that would be the reaction right there. And then which salt has greater value of KSP? Which one has greater solubility constant? AgBr or AgI, justify your answer. And what we see here is that we would say that the AgBr, okay, has a greater value of KSP. Has greater value and the question is, how did you know that? Well, when you think about this problem, you know that when you mixed NaI and AgBr, which by the way, AgBr, we've done all this work on, we actually do know the KSP value for, you see that you would get AgI solid from cream to yellow. So you would see that you get an actual precipitate of AgI. So that means that the solid AgI in terms of AgI's dissociation equilibrium, okay, the equilibrium is highly shifted toward producing more precipitate than the respective dissociated ions. And if that's the case, then we know that the KSP for AgI must be small because the ion values that are actually part of KSP calculation are very small values, as they would not be being produced in large amounts because the precipitate is being favored in the production when we did the double displacement reaction. So AgBr must have a greater value of KSP than AgI because, okay, we see AgI solid formed despite the presence of BR minus and AG plus, right? Also in solution. Of AG plus and BR minus also in solution. Okay, so big idea is that you just, because you got the solid AGI precipitate, you know that that is going to have a smaller KSP value in order for that precipitate to have even been favored to form. Okay, so and that means then that the AGBR has a greater value of KSP because it is more soluble. All right, that is the end of question 1, and it was a long. And so, by the way, that should have taken you, if you were to do this on the AP exam, they give you 23 minutes to do a long question. So, best of luck. Good work, you guys. And hopefully these walkthroughs are valuable to you. I'm actually realizing they're quite valuable to me to actually help you understand what you might see when you first encounter these FRQ problems that you maybe have probably not ever seen before. So really good work, you guys, and have a great day. Bye.